Hi. Can you guys hear me? Okay. And Dakuba, can you hear me?
Yes, Prof.
Oh, good. All right. That's good.
I can hear you.
Yeah, I got your email. Anyway, if anyone has problems with the grading, just let me know and I'll go back through it. Like I haven't looked at your thing yet, but I'll look at it. So, because the grading, I mean, it's pretty arbitrary, so you can kind of make an argument. I mean, in the end, probably everyone's going to do okay in here. But so anyway, so this one, yeah, the grades on this one, I think one group got a 66. Good. And it was a group that had 4 people in it, and then everyone else got a 90s or 80s. That's okay. Anyway, the one group, I don't know, maybe it was just like who knows. But basically, again, like if there's any questions about the grading, just come back. I try to put some notes in it, but so I want to go through this. So one thing on tacticity, so you can't say like on the side, like you can't say side, like the word side, because like say you have your hand, right? My thumb, that's my right hand, my thumb's on the left side. But if I flip it, my thumb's on the right side, right? And you're talking about carbon-carbon bonds. So these can spin around that. So whatever your R groups are on this thing. So you can't say this is at the bottom because that can spin. There's no bottom top, it spins. So you have to say, you could say like handedness or whatever you want to say. But if I said like my thumb's on the right side, so I could say my thumb's on the right side on my left hand too, but they're different. They're stereographically different. But anyway, so that was a problem with this question about describing tacticity. And then I guess I like, if you say atactic, like commercially, it just means there's no preferred tacticity. Like you say polystyrene is atactic polymer, it means there's no preferred tacticity to it. If you want to strictly define it, if you say it's random, then you have a statistical thing and you say 50% mesoracemic. And then you could go to the isotactic should be 25%. The syndiotactic should be 25, and the heterotactic should be 50, because these are MM, RR, and RM or MR. Like in other words, you're flipping a coin. Is it heads, heads? Is it tails, tails? Is it heads, tails, or tails, heads? There's twice as many chances to get tails, heads, heads, tails than there is heads, heads, or tails, tails. Right. So these are less likely to happen because there's no order. The order of this doesn't matter. So, and then if you go to pentad, so the way this works is you have for the dyads you have 1, 1. And then for this you have 1, 2, 1. So you have iso, syndio, hetero. Then if you go to pentads, it's going to be 1, 3, 3, 1. So that's called the Bernoulli triangle, I think. 1, 4, 6, 4, 1. Like this is for triads, pentads, heptads. So you can figure out what the distribution is going to be with that triangle. That's the part of statistics, right? Say, so if you just have a coin flip heads, tails, it's 50-50. If you have triads, it goes 1, 2, 1. Anyway, so people that do tacticity end up doing this kind of statistical thing. Then if you, and I said this in class and nobody got it, but like if you have a persistence like, and it's like, if it's like 6 or 7, right? And then, or 7 mer units, like C infinity is 7. So whatever C infinity is, that's how many mer units are in this thing. So basically, a heptad would be the lowest thing, like this 14641 would be the lowest thing. So triad would be 3, heptad would be like MMR, MR, right? So this is triad, pentad, heptad. So it's 4 of them. That would be this for polyethylene, that would be the smallest tactic unit that would be of interest to talk about for persistence. So the dyads are useless, like totally meaningless. The triads are kind of meaningless. Pentads are maybe a little bit better. Heptad is the lowest one you want to consider for persistence. You probably want to consider like nonad and whatever higher. But it's difficult to get heptad on an NMR. So basically, without doing computer simulation, you can't really start predicting these things. You know, you can't really connect tacticity with the properties. And then this is just the Kuhn unit, right? So if you want to go above the Kuhn unit, so say you want to crystallize, and you have to have a huge number of these. So the triad tacticity isn't anywhere near enough to predict, is it going to crystallize or not, or is it going to form a helix? Right. So that's where the computer simulation allows you to get the whole picture, even though it's not a real system. At least it gives you an idea what's going on. Any questions on that? I mean, it's kind of a simple question. People lost points on it. Like anyway, that one's the easiest, and this is probably the hardest, the second one. So this opals, so then it's like, what is opals? I wanted you to, I said give short answers, but basically I wanted you to at least like look at the web page and kind of get that like write this energy function, say like what the terms are in this thing, you know. So each of the, like this is just a spring constant. These two are spring constant equations. And I even say that in the question. No one, I think nobody really got that, you know, so it's kind of funny, but I mean, I think I said, see, I said force is dE dx, the spring constant is that. So if you take the integral of this, you get x squared. So that's where this x squared thing comes in. Where did they put that from? Here? No, here. So that's why this is squared, because it's the integral of the spring constant thing. Then this is a dihedral. So we talk about dihedrals in this paper. So it's important to have that term, so et cetera, right? So you could say whatever stuff about that, but mostly like one group gave a lot on that. It was good. I probably should have given you extra points. And the others, anyway, there was in between almost nothing. And then like one of them, the one that gets 66, it was just like wrong what they said, you know. So anyway, and then the cutoff distance, the idea of that is that you're talking about measuring potentials, binary potential interactions, right? So if you're basically making a sphere, so it's going to be like r squared equals the number. So if r goes up by a factor of 10, it's 100. You have 100 more, and if it goes up by a factor of 100, it's 10,000. Right? So your computational weight of the thing goes nuts. It's a geometric, it's not a linear with the distance out. So basically you have to have a cutoff point. And also this 612 potential is going to be like, it's going to be decaying down to 0. So the high end ones don't matter. They disappear anyway. So it's basically, you say I got a cutoff there. I won't have to do the 10,000 calculation. Plus the value of that thing's minuscule compared to the big values of it. Right. So like this would be potential energy versus R curve. Right? So anyway, so that's the value of a cutoff. Some of you kind of got that. That was okay. Leapfrog algorithm. I mean, that's a nuance. So okay, anyway, there's a link to it, and you guys basically got that this leapfrog thing. And it's basically like you take a step, you know, the position, take a half step for the velocity and use that to move the position a whole step. So you're kind of jumping back and forth between velocity and position. Right. That's kind of the idea. So anyway, it's kind of somewhat of a simple idea, but something you probably never heard of. And then the steepest descent method, this is something you should have seen, like the Cauchy method used in the 2D to get, so you have, you're going to have an intercept. So you write your equation, blah, 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 equals blah, 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 blah. And then you got to say blah, 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 minus, so like A minus B equals 0. You set to 0, you try to find this point here. And this is some curve. So you find like, oh, I'm going to take the derivative of the curve, and I'm going to go until the derivative times x. So dy dx times x equals 0. So I find the intercept. I project where the intercept would be. So it could be some like crazy intercept. And then you go back to the curve at that position, and you see what your value is from the function. Y equals some function. Is it 0? And then you say no, and then you take the slope there and project where it goes. You keep taking the slope. So you take the steepest descent at the point where you are and find the position. That's the Cauchy method to find that solution to this equation. Just some complicated equation you can't solve. So you just say A minus B, and I'm going to take the derivative of it. And then try to find where that goes to 0. And that'll be my magic X value, wherever that solves the equation, right? And that really describes it very well. But basically, do that in 2D or 3D, and then you have a surface instead of a straight line, and then just find the gradient of the surface, like the gradient of the function. So there's a thing from Purdue that where the guy gives a video of that and describes it pretty well. I think steepest descent thing. I think one group looked at that and kind of put it from that, and the others. Anyway, it was okay, mostly that. The ensemble things, you have, so you have the canonical, and then somebody said NVT. So the V part's important. You're holding V constant. So that means you have a lattice, a fixed lattice, and you have your beads on it, and they move around with this potential, but the lattice still stays the lattice. Like the lattice doesn't grow into a bigger lattice. Right, that would be a delta V. You don't have that. So if you don't have delta V, which is what happens in nature, you have a Helmholtz situation, like Helmholtz free energy. So like A. And the thing that you usually want is the Gibbs free energy, G. Right. In other words, if you want the chemical potential is dG dnx. Chemical potential of component X is a change in Gibbs, partial Gibbs with respect to the number of moles of X in the system, say, right? So if you want to know chemical potential, you need Gibbs. If you're doing computer simulations, you have Helmholtz, and they relate by, you can use the thermodynamic square. All right, so you say A is V, so A equals, so G equals A plus VP is G, right? So you need to add VP to this Helmholtz free energy that you get if you want to get the Gibbs free energy to get the chemical potential. So if you're doing a simulation or a modeling with a lattice, then you get the Helmholtz free energy. And then if you want to get the chemical potential, which is the thing that drives everything in the real world, they need to add the volume times pressure to it to get the Gibbs. Gibbs is the A plus VP, and then you can do the derivative of the Gibbs to get the chemical potential. And you can say two components in a system, the chemical potentials are equal at equilibrium. Anyway, so that's why this canonical ensemble is used, because the systems are fixed in volume, not fixed in pressure. But in the real world, we're at atmospheric pressure, so we have a fixed pressure and the volume changes, so you get thermal expansion and things. All right, so that's a long answer to it's kind of this thing. And then that's it for that thing. So that's the idea of this. There's a lot to it, actually. So anyway, people lost points on this part. If you want to argue points, we can do it. That's fine. I'll look at it. I mean, I encourage you to argue points on this, whatever, any part of this. Any issues with that one, the number 2? Okay, so then Equation 1 is this thing. Just got the vector. So you have your chain, and you have a position k. So it's going from I equals 1 to n, and here you have I equals k, some position. So you have the vector, like the tangent to this thing, right? It's going to be a vector r k, that position k. So say position k is there, r k, and that's got a value, but basically you can remove the value by dividing by just the magnitude of that. So you make this a unit vector. And then the chain, whatever it is, has an end-to-end distance, r. Right? And that's a vector. So it's pointing in a certain direction. It's wandered away. It's a random thing, but basically it's pointing in some direction. So you dot product that with r. You say, so you can take the average over 100 chains for that same, because they're all the same chain. So these chains, r is pointing in all different directions, but for that chain, you dot product between that. So it's like the cosine of the angle between the two, and then times the magnitude. So the magnitude of that is 1, and then the magnitude of r. All right, so the end-to-end distance. So if your chain's a rod, then all these r vectors are parallel to that. So the angle is 0. The cosine of 0 is 1, so you just get r. So for a rod, LP equals r. If it's totally random, then all these things are pointing in random directions, totally random directions. I think that's not really going to be possible because they're glued together, right? But if they could totally randomly point, then your LP would be, then the average of cosine would be 0, because cosine is a symmetric function, like the plus and minus are the same. So if you are averaging both sides of it, you end up with 0. So then LP equals 0 for that case, for random. But you can't have random because they're glued together, right? Because they connect each other, so that if you're pointing this way for k, then k plus 1 is going to be likely almost pointing in the same direction, right? So that means they're not random, at least not locally. So locally, you're going to get some correlation of it, and that local correlation is going to result in the persistence length coming out of this thing. So that's the kind of thing I wanted you to say, I guess, for that. You can also one group justified this function in words, which was good. That was pretty good. Anyway, there are varying degrees of kind of saying that. Some people didn't understand that this was averaging over all the 100 chains in the system. Some people didn't know what the K was talking about. So the K is the index along the chain. And hopefully you can see that, this isn't unique to this paper, so these are the common terminologies people use. So I think that it's good to kind of, even if you got it wrong, to figure it out, and then it'll help you later. Any questions on that thing? Then so the two papers, so they get different values for the so I'm looking at this plot, and they get the only thing that you can compare is isotactic polypropylene, syndiotactic polypropylene, right, which is the blue and the red, right? So syndio's got a higher persistence length, and it's like 12, and it's something like 7, right? 7 and 12, and the ratio of that is like 1.65, I think. And if you go to this guy and find the same plot, it's here. So he's got syndio and iso, and it's, instead of 7, he's got 11. Instead of 12, he's got 18, and the ratio is like 1.8. So it isn't like this scales. Like, in other words, there's an error in this that's just a factor. It's like they don't have the right number for these things. They get that the syndio is stiffer than the iso, but they don't get the proportionality between the two. So I think that means there's a problem with this thing, that the two things aren't. This is a single chain, and this is a melt. People talked about that. So the answer for this was pretty good. I think people did okay with it. Basically, the numbers aren't right. So, and Chen's numbers correlate with literature values from measurements from neutron scattering. So people got this question pretty well. The dihedral thing, that was kind of disappointing, I guess, but I wanted you to kind of look at that, this thing, like this is the origin of it, the protein. So you have the idea is that, so I wanted you to go back to that and say there's two angles to this thing. So we have so this is called the alpha carbon here that connects the two things together, right? So that's not the alpha carbon. Yet that is the alpha carbon. All right, so basically you have, in our case, we have like a carbon, our alpha carbon is kind of that carbon, and there's two carbons with this methyl group on the side. Right, so this is the way I'm looking at it. So this thing's, this is the rotation angle of that methyl group and this methyl group, and they're relative to the same carbon. So there's going to be like a phi and a psi for these two things. There's a methyl group and a hydrogen sticking off. And this guy's got two hydrogens. So if you look down that way with your eyeball, then you'd see like you can do with the Newman projection of it like that. You have your R group. And then you could also look the same thing that way. So you're going to get two different kind of angles to this thing. Right, there's two angles because you have two Mer units together. So you're doing a dyad. This is the same thing as a dyad, right? So that you're getting 1 point for every dyad in this thing. So that didn't come out in anyone's answers, you know. So I think if you looked at this, you kind of figure out the origin of it and why you're doing this plot, which is to see that if these things are, certain arrangement of these will give you alpha helix and a beta sheet, the two main kind of things that are in proteins. In our case, oh, it's here. So in our case, he's getting, this is the planar zigzag. When they're both 180, that means, so if you have polyethylene, the chain is literally lying in the plane because the hydrogens are sticking in and out like that, like in, out, out, in. And the lowest energy conformation is just lying down. Right, so and these are all hydrogens. So basically there's nothing to hinder it from going to that lowest energy all trans state, which is just a planar zigzag. So the angles here are all 180. So if it's 180, 180, that's a planar zigzag, that's polyethylene. And if you get into these different helices, because this isn't, one of these is a methyl, then that kicks it over, then it can form either a left or right helix. And if depending on the tacticity, so depending on isotactic or syndial. Right, so as you're going along the chain, for all the dyads in the chain, you get 1 point for each dyad, and those points add up to either trying to form a left or right helix or trying to form a planar zigzag. Right, so that's kind of the picture that this thing has. And then he skips along these are for the different positions in the chain. So he shows here, like where is B, A, B, C, D are. These are these A, B, C, D here for these chains with different odd groups thrown into them correspond to these A, B, C, D here. Right, so anyway, so that's kind of the picture of that. I don't know, people did okay on that question. That's about it, I think. So the dyads correlate with certain kinds of helicity, and then you can map it out with that. That's more or less the point of the paper. Any questions on this? So I think people did okay, except the 66 group didn't seem to put as much time in it, but maybe I'm mistaken on that. But anyway, okay, so everyone's happy with that. So if you have problems with grading, just email me and I'll try to work through it. At least justify what I did, and if I may modify the grade, you know. if you argue enough, I'll give you points. It's the bottom line. So that I'm not really married to the grades. Okay, so all right, so I wanted to move on here a little bit. Actually, I wanted to kind of go through what I did last time, because it's important, and it's better to go through it again and give you another, like an overview of it. And then I wanted to go through two things that are in the paper, the rate of gyration and the osmotic pressure. So I just wanted to restart this thing again, just kind of zip through memory lane. Not this one, sorry. Let me go back to 21. This is slides 3, osmotic pressure. And the one we're working off is slides 2C, which is the next one on the web page. Let me show you that. So you have at the top, the first thing is like 1 we're done with. Then long range, that's 2C. And then 3 isn't this. Let's see. Traditional side power dynamics. I'll have to figure out where 3 is. Perturbations of the chain is 3. Right. So if you look at that one, it should be the same if you go to 21 or something in this. So it's after, we'll talk about the beginning. See, osmotic pressures here. So that's in osmotic pressures in this slide 3 thing. Right. So anyway, so let me go back here to 2C, right? So anyway, so I wanted to, so this van der Waals, and turns out it's not in any of the books, right? Basically, this turns out to be the basis of the whole operation. And it's much easier, should be much easier to understand the van der Waals than it is to understand the Flory-Krigbaum equation. Right, so van der Waals is kind of simple. It also ties to osmotic pressure. Okay, so let me just say, if you have a gas, right? So why does it have pressure? Because the atoms are moving with kT energy, right? And then they hit the walls. So the kinetic theory of gases ends up giving you this ideal gas law. PV or P equals rho RT, right? Rho is the atomic, the number per volume. And that rho is kind of the common thing to use. It's unfortunate that rho is also used for density, right? And it's kind of a density, it's number per volume. So basically, you get that from the kinetic theory of gases, and it's kind of easy to derive, but basically you're not going to do it, right? So that fails. So if you plotted the P versus V, because P is proportional to 1 over V, then you get this kind of swooping thing. If you plotted P versus 1 over V, it'd be a straight line, right? But so you get this kind of decaying function. That's ideal gas. That isn't how. So there's no phase separation. There's no liquid, right? And also, this allows the atoms to pass through each other. So you need to add in this excluded volume. So this is where the excluded volume term was introduced. Is the idea that in van der Waals you have to exclude some because atoms can't pass through each other, right? And then if you want to have phase separation, you need to have an attractive enthalpic interaction. You have to have the things. So you have to have something that attracts the atoms together so they can form a second phase, right? So you add in this A term, the A term. So this B reduces the pressure. B increases the pressure because you're excluding some of the area where the atoms are, so they have less space to move around with kT. So that goes to the wall, gives you pressure. Pressure decreases when you have them attract. So you have to have a negative attractive potential, and it's a binary potential. So you have the density squared, number per volume squared, because the probability of finding 1 is the density, the probability of finding 2 is the density squared, right? And that times the potential for a binary interaction reduces the pressure, right? So that means that if you have right, so we have that's the van der Waals equation. That's an expression for pressure and volume, right? Another expression for pressure and volume people talk about the compressibility factor, which for ideal gas would be 1. So PV over RT or P over rho RT is 1 for ideal gas. And then we compare it with this van der Waals expression for PV. And then you can solve for the, if you do a viral expansion of that, it's like a Taylor series expansion in density. So you have 1 plus the second order term, which would be B2, which is accounted for here kind of with A and B. So A and B are dealing with how the particles interact with each other in a binary way, like one acting with another. This is binary, so it's rho to the power 1 and then rho to the power 2. So that's called the second order. The first order would be the ideal gas, and then you have the second order, right? So anyway, this B2, you can solve it with this equation, and you find out that it's it equals the excluded volume minus the attractive potential by KT, right? So that sets up for what this viral coefficient would look like. Then when do these, so it's possible to have these kind of interactions like disappear, okay, because B2 represents the binary interactions that can go to 0 when you get to a magic temperature, this T star where A is A over RB. So A over KB gives you this magic temperature where you get phase separation as you cool it down. You'd reach that temperature and then you get the phase separation happening, right? So this van der Waals equation introduces the idea that you could have a phase separation because it's got a temperature dependent term and a non-temperature dependent term, right? So kind of a excluded volume and attractive potential. Okay, so anyway, so B is going to have a temperature dependence. It's going to be 1 over T. And it's also going to have this kind of excluded volume number involved in it, right? And that same model is used for polymers, exactly the same thing. Okay, so in polymers, you can write the energy by comparison of the Boltzmann to the Gaussian distribution of the end-to-end distances. You say it's thermally caused, so you can write an equation for the energy of the chain like this, making the arguments that exponentials equal. And then if you want to, so that's ideal, that'd be an ideal chain. If you want to include excluded volume, so the B term of the van der Waals, then you say, what is the probability of excluded volume? For one unit to exclude another, it's the volume of a unit divided by R cubed. 1 minus that is that it didn't exclude, and then raise it to the number of pairs, which is n minus 1 over 2 factorial, which is n squared by 2 if n's big. So that probability is multiplied, so you raise it to that power. And if you want it in an exponential form, you take a log of this, log of something to a power, the power comes out front, and then you have exponential of this thing, this ln of 1 minus. If you can expand exponential to 1, if exponential is small, which it is, like VC by R cubed is a very small number. So then exponential of x can be expanded to 1 plus x squared over 2. Take the first two terms, and then this 1 minus, so x is minus VC over R cubed. So we have exponential of minus VC over R cubed times n squared over 2. That's our excluded volume term, right? And it's of the same form as our exponentials up here, so we can just add that into this energy term. As you equate the argument to the energy argument from Boltzmann, then you just get plus this n squared over VC, because this is a negative here in the Boltzmann, so it becomes plus, right? So that's our energy for an excluded volume chain. And then basically, so if you have that energy, so in order to get R squared, right, we wanted to get like R squared, you get that from the probability function times R squared and integrate it minus infinity to infinity. This being the Gaussian probability function, dr. Okay, so that gives you the average R squared, which you said we found out was NL squared in the case of a Gaussian chain. Here it's not going to be NL squared because P of R isn't that exponential, and this integral can't be solved. So that function, so our Gaussian looks like that. If you multiply it by R squared, R squared goes to 0 at 0, and then this thing decays, but R squared increases. So you're going to end up with this kind of peak function, right? And that's the thing you're integrating to get this R squared, but you can't integrate it because you've skewed this distribution function. So you take the derivative find the point there. And Flory-Kriegbaum found out that that gives kind of the same answer, so the derivative gives the same answer as the integral, and the derivative gives you this function. All right, so they couldn't analytically integrate this function, but you can integrate it with a computer, right? So you can just do an integral with a step with this function, and then you can integrate it and get these red dots. So you can actually integrate this function before you make the approximation. You're going to use the derivative instead of the integral. And that will give you an answer. And that's just the red dots here. So you can see at low end, so you have to have a chain above 100 to get the scaling behavior. And then the NL squared scaling behavior is this red, so it deviates from that. So you can see the expanded coil R squared is larger than the Gaussian. And then Flory-Kriegbaum wanted to analytically solve this. So they said that if you expand this out, you'll get that you get the fifth power and third power. If the coil's expanding to a large size, you can forget about the third power and keep the fifth. And then you can just solve this thing to find out that R star is going to be into the 3/5 power. Right. So there's an approximation involved in the 3/5. That approximation is the difference between the blue one here, which is 5/3, and the red one, which is the actual integral. If you do molecular dynamic simulations of self-avoiding chains, you get the green one, which has a slope of 1.70. This is 1.67. This is 1.70 from computer simulations. And if you just do a power law fit to the result of a numerical integration of the Flory-Kriegbaum, you get 1.72. Right? These are all kind of within, you can't really discern those differences between those. Basically, the 1.72 seems like a pretty good number. So people talk about nu is a scaling factor from Flory, and that's 1 over this fractal dimension. So that's going to be either 3/5, so 0.6 for Flory-Kriegbaum, 0.588 for simulations, and 0.581 for this numerical integration. Right, so usually this 0.588 is a number you'll see people using because it came from simulations. If you're doing simulations, people tend to stick with that. All right, so there's that business. Any questions, interrupt me, but so this gives the idea that there's 2 states possible. Like there's only 2 states possible because this excluded volume is either there or not there. If it's not there, you get Gaussian. If it's there, you get 5/3 power, 5/3 fractal dimension, right? So it's either on or off. There's no like in between. But if you look at the data, you can see that there is no on and off to this. The theta state, in fact, is this tenuous state as the coil's collapsing. So there's a point as you're dropping temperature where the coil collapses, and somewhere in the middle of that collapse is the theta state, where you can find that basically where you find this condition of like for the rate T star that's A over B, that kind of position. That temperature would be right at the middle of this collapsing thing, right? So it's phase separated here and it's collapsing there. And then the expanded one is gradual, and there's different kinds of expanded, right? In other words, it gets larger and larger, and finally it reaches a plateau. It depends on how you measure it, and I'll talk about rate of gyration, hydrodynamic radius after, but basically it's not going to reach a point. So you need to consider that this thing has a temperature dependence, this excluded volume, and that's pretty easy to get. You find an average energy and just say it's a Boltzmann probability with that energy term, and then you find out that's an exponential. So this can be exponential, can just be added into the energy. And you find out that the form of this is exactly the same as this form, except there's a difference of a factor of 2. So you have the 1/2, and the energy term is this chi, which depends on 1 over T. So this starts to look a lot like the thing where you have an excluded volume B, and then this attractive potential A is chi. Chi is an attractive potential between the Murr units of the chain. Right, so we get that expression for this expanded coil energy. And then if you plug in that, if you use that, so that means we have the excluded volume is actually the volume times 1/2 minus chi, and we can just plug that into this expression we had, the Flory-Kriegbaum simplified expression for the coil size. We get this expression for the coil size, and that's what these curves are. It matches perfectly with the data. So we have a perfect match, and we have a thermally changing radius of gyration that gradually goes from the theta condition to the expanded coil of this, right? And that's kind of the Flory-Kriegbaum thing. All right, so then I wanted to go to slide 50 of this thing. So I wanted to, because the paper we're dealing with talks about talks about radius of gyration. So this is pretty quick. So what is the so if you have a coil, right? So you have a polymer coil. So what's the size? So we said we can get the end-to-end distance, r squared is NL squared. That's one size. But say you have a coil that's got branches on it, right? So it doesn't have, it's got a lot of end ends, right? There's a lot of different end ends in the thing. So the question is like, what is the size in that case? Or in general, what is the size of any kind of thing, anything, you know? So radius of gyration is a way to get around that. So you say you have a center of mass. So you have the center of mass would be found at this position, our capital G, which is 1 over the number of mirror units in the chain times the sum of all the positions. R here is like the position from some arbitrary origin, like those positions. So sum all those divided by n, it gives you the position of the center of mass. From 1 to n, right? And then you want to find for every position in the chain, so Rn, subtract it from the center of mass position and square it, right? And then take the average over different chains, sum that over the chain, over the same sum that you did the RG thing with. And then you can get this and reduce it by the number of units, and that gives you this RG, radius of gyration squared, because this thing's squared here. Right, so that the going that way and that way cancel each other, and you get that. So what does that look like? It's going to be like somewhere you have the end-to-end distance and somewhere in between. In fact, RG squared is going to end up being R squared over 6. So once it's going to be, I think 2.45 times the end-to-end distance. So somewhere in between the end-to-end distance and the center. So it's going to be smaller than the coil size. But this routine of summing, finding the center of mass and then summing over all the units, that can be done for a branch chain. It can be done for any kind of chain. So this becomes kind of a robust way to get the size of a chain, right? So if you plug in like the NL squared for this end-to-end distance, and then you can work through the math and get this 1/6 thing from it. 2.45 RG is end-to-end distance. So it's like 1/3 of the end-to-end distance of the chain. To measure that, if you do scattering, so to measure the intensity versus the angle, and Q here is 4 pi over lambda sine of the angle by 2. Let's say you shoot a beam and it shoots off at an angle, measure the intensity, right? You do a log plot of that, then you get this. This is basically a Gaussian decay. So if you have a Gaussian curve in Q, it's going to be exponential minus Q squared RG squared over 3. That's called Guinier's law. So it basically means that the curve's Gaussian in Q. And the weighting factor of that is radius gyration. So basically you can measure it directly in a scattering plot. You can see it matches best at low angle. So this is neutron scattering, but at low angle, like if you take this all the way down 3 orders lower, you're in light scattering. You can measure this slight curvature of that even down in light scattering. So you can use light scattering to get the radius of gyration of the chain of anything, of any kind of object. right? So I'll talk more about that later on, but I wanted to do something else first. So that's in the paper, radius of gyration. Just want to mention it. Any questions on that thing? Then I wanted in this paper also, I wanted to mention osmotic pressure he talks about. So this has to do with the coil chain scaling also, but so if you have, say you have a gas, right, and you just have gas atoms that has a pressure, no atoms has no pressure, right? So the pressure here is the pressure is the density number per volume times kT, ideal gas law. Okay, so if you think about putting a colloid in, so you have something floating around in water or in some solvent, or they could be charged, not charged. Then if it's a polymer in toluene, then basically each of these black dots is a polymer coil. And there's a pressure that's created because each of these polymer coils is moving around with kT. Right? They each have kT that move them around in the whatever they're in. Right? So they're hitting the walls and they create kind of a pressure. So that's called the osmotic pressure, and they call it pi to distinguish from real pressure. So if you take put a semi-permeable membrane that allows the solvent to go through, but not the polymer or any kind of colloid, it could be just a glob floating around, right? Then the solvent wants to dilute this thing, right? So it drives, or you can think of it that these things move around kT, they hit the walls. It's like a kinetic theory of gases model, creates a pressure, right? Or you could think of it that the solvent wants to dilute these things so to equalize the osmotic pressure, the chemical potential of these blobs on each side, and there's none of them here, or the chemical potential of the solvent on each side. So it wants to dilute this thing by driving the solvent over, and that will raise this fluid up here. The difference by MGH gives you the pressure. Like you can measure this pressure just with a tub with a membrane crossing it, and then two tubes. Measure the height, and that gives you this pressure. So that'll give you the number. If you know the number of units, so that'll give you the number of these units in this thing. If you know the mass that you put into it, like when you weighed and made the solution, then you get the molecular weight of each of these things from this thing. Because if you know the number, you can get and you know the mass you put in, you can get the mass per blob, per whatever, per polymer. Right, so this is a way to measure the molecular weight. It gives you the number average because it's a number. It's a counting method here. Colligative, they call it a colligative measurement. So colligative means you're counting the number, right? So that's what osmotic pressure is. You can also calculate osmotic pressure, and in the paper we'll look at tomorrow, go through like how they do that with a computer simulation. But so anyway, since the PV is like energy, so you kind of have this viral expansion of the osmotic pressure. The same thing as what you had before for actual pressure. Right, so you have the first viral coefficient, second viral coefficient. So because if you're going to use chi for B, so chi is per monomer, right? This is an energy per monomer. So you have energy per monomer for B2 from the Flory-Krigbaum theory. So that's what came out of the Flory-Krigbaum is B2's 1/2 minus chi. Then rho is the number of polymers per volume. So you have to divide by n here to get the number, to get this on monomer terms. Right, so basically this n accounts for the fact that each thing that you're measuring is a polymer composed of n units. So you have to kind of reduce the number of monomers by n to get the number of polymers. It's actually giving you the pressure. Right, so this n modification of this equation is because it's a polymer. And then B2 is this 1/2 minus chi for the case of osmotic pressure. So this is a way to measure both the molecular weight and the chi interaction parameter if you get the second order term for this. So this predicts that if you plotted pi over kT, that you get a straight line. So if you do a plot of pi over RT and divide by concentration, so then that should be flat initially. The flat part of this will give you the molecular weight. and these are for different molecular weights. You can see that shifts with molecular weight. Then the high end part should go with this concentration squared if it's Gaussian chains. Right, but the power there actually is not 2, it's 9/4. So power 2 would be phi to the 8/4, and the actual is phi to the 9/4. So it's slightly steeper. You can see the projected for the Flory-Kriegbaum is that straight line, and this is the actual one. So it's got a significantly higher pressure, and that's due to this expanded coil behavior of the thing. So you can get that by saying that you have the ideal equation, so the phi by n, that's the molecular weight dependence, which works. So the molecular weight dependence works fine here. The pressure goes up with molecular weight, and then this part doesn't work. So you have that part, you're going to have that this part happens when you get above the overlap concentration. So overlap is 10 to the 1. So C concentrated by overlap concentration is 1 here, and that's where you start to see this. So this effect happens when the coils are like interacting with each other. So in that region, you can't see an individual coil. So you want to have concentration divided by C star as a natural parameter. You say that's a power law dependence because you see it's a power law out here and C by C star. So you want that dependence. So the question is, what is that P? So C star equals the mass divided by R cubed, and R to the df equals n, right? And df is 5/3 here, is R to the 5/3, or n to the 3/5 is R. So if you have R cubed, this is n to the 9/5, and this is n to the 5/5. So you end up with n to the -4/5 power from this good solvent scaling from Flory-Huggins. Flory-Kriegbaum sees n to the -4/5. And if you say that this pi doesn't depend on molecular weight, so this should be to the power 0, then it's p times 4/5 minus 1 has to equal 0. If you solve that, you find out that p should be to the 5/4, and if you plug that back in here, then you end up with pi to the 9/4, which is what's seen in the plot. Right, so that's kind of seen as a demonstration that the good solvent thing works, that business. But anyway, so that's kind of the whole show on the osmotic pressure. So that's kind of where I wanted to get to today. This B is 1/2 minus chi. You can get by comparison in the equations from this thing, right? Or you can actually derive that if you want. So to derive that, the way that's done is you say that you have all right. You need to have the Flory-Huggins equation for the free energy of mixing. So the Gibbs free energy of mixing. Or this is the Helmholtz free energy of mixing, so it's missing the PV. So if you have the Gibbs, so the Gibbs is the Helmholtz PV using the thermodynamic square. So the Gibbs is Helmholtz plus PV, right? And Helmholtz is Gibbs minus PV. So Gibbs is Helmholtz plus PV. Helmholtz is what you have from that because this is a lattice model. So it's the constant volume. It's a constant volume lattice, so you don't have the pressure change. So, and the pressure is what you want to get out of this, the osmotic pressure. So it's important to have that. So basically, this is the Flory-Huggins. This is the polymer concentration. You need to divide by n to get the number of polymer molecules. This is just the ideal gas mixing law, and then you have a binary enthalpic interaction term. So that's called the Flory-Huggins equation for the free energy of mixing for a polymer in solution. So you take that thing, and then if you want to know the osmotic pressure, you want to know the chemical potential of the solvent with the polymer and without the polymer. You want to equate those two to solve for the osmotic pressure between the two cases. Like in other words, how much does the liquid rise in the system? Then you need to calculate that. That's going to be the derivative. That's going to be the derivative of the free energy with respect to composition. And then it's going to have this P plus pi term. So you can solve for pi from this if you calculate these two chemical potentials and equate them. And then the derivative of that's done here. And when you do that, you find out that this is the expression you get for pi from equating the two chemical potentials based on the Flory-Huggins equation. And you end up that the first term, this B2, is going to be 1/2 minus chi. So that's kind of where this, that's how Flory derived this thing, this 1/2 minus chi term here for B2. You can also do it just by comparison of what we did before. So that's about it for this. It's a lot, but basically this is all, that stuff's in the paper, so I wanted to go through that today. Any questions on anything? I'll go through the paper kind of related to this, related to this stuff and related to the things we covered in this slide 2 thing. But so it was in here tomorrow. And on Friday. I should be in on Friday, I hope, but we'll see how it goes. All right, so that's about it. So
if you're not able to come in on Friday, is the tour still going to happen?
I don't think so.
Okay.
I mean, I think I'll be okay. It's got to be okay, right? I'm going to test tomorrow morning, and I'll let you know.
Yeah, I want to make sure you're okay. I was just wondering. Okay.
I'm fine. I feel fine. It's more like spreading it around.
Yeah.
It's not me really. And I'll be wearing a mask too, so it should be all right, I think. But
that's fair.
I don't know about riding with me in the car. That's kind of dicey a little bit, but it might be okay. I mean, I'll wear a mask in the car too if anyone needs a ride. So far, I only have you, I think.
Yeah, I have my own car, so I can just drive myself.
Okay, and Yashmita, are you going to it or? Yashmitha. You said you wanted to go, I think, right?
Yeah, Prof, is it this Friday?
Yes, tomorrow. I mean, yeah, this Friday after, it'll be like 12:30, we'll leave UC.
Oh, okay, it's fine. I'm interested. I have sent you an email to that.
Okay, but you need a ride, right?
Sorry?
You need a ride to the thing.
Yeah, I do.
Okay, so Carter, do you have any space in your car? Or are you coming back to campus? That's the question.
I'm gonna actually end up driving home after, so I wouldn't be able to.
Okay. All right, so you can ride with me, but you're gonna have to wear. Do you have any masks?
Yes, I do.
Okay, wear a mask. Wear a good mask, like an N95, whatever mask.
N95. Okay.
Do you have one of those? Or?
I don't have.
All right, I'll bring one.
Okay, sure.
Anyone else need a ride or? Yes,
I know Noah had talked to me. I don't think he was able to make class today, but talked to me about it. So
all right. Okay, well, yeah, we pretty much have to know tomorrow or some. Yeah, I gotta send him a list of names, right? So
okay. Yeah, I can text Noah.
Okay. Carter, Noah, Yashmitha, I'm pretty sure wants to go.
Yeah. Yeah, I'm 100% sure with Noah, but I'm just confirming.
Yeah, are you going tomorrow on Friday?
I'm going.
Yeah, you are, but what about Yashmitha? She just.
Oh, sorry. Okay.
I have a graduate seminar at 12:30, so I don't think I can able to come at that time.
Okay. You gotta fix your mic, your mic doesn't really work. All right. I mean, maybe we could push it back a little bit. 12:30 seminars at 12:30. I wonder if you could get on. What's the seminar?
No, I think it's a compulsory seminar that we normally do Fridays.
Yeah.
So can you skip it or something? Or can you tell her that you're going on this tour? If it's a good subject, I don't want you to miss it, but the tour is kind of like a seminar, so I think they'll let you swap it.
I will talk to that relevant officer and I will let you know.
Okay. Yeah,
Maybe, Prof, I don't know if you can help share the email to the, I guess, the lady that the prof that's in charge of the seminar, so
yeah, I
that
can do that.
that she will know that part of the us that are doing
Yeah, I
what
can do that.
colleagues are going for, yeah, for a talk.
So what, let's see. All right, yeah, I can do that. It's Ashley, right?
Yeah.
Is- Okay,
Yeah.
so I can send her an email.
Okay, thank you.
So if you want to, but Yashmita, are you in chemical or are you in materials?
Please tell me.
Okay, so there's a chemical seminar at 12:30 too? Oh, is it chemical engineering seminar at 12:30 or is it materials?
It's not that chemical engineering.
Okay. Who's running that one?
It's Professor Peter.
Okay, I can email him, I guess. Or her. I couldn't really hear. I can't really make out what you say with the mic, you know. I mean, do you want to go, or if I could email them, can you send me an email with who it is and like what I have to do? And I can send them an email.
Okay.
Okay, that'd be good.
All right, Professor. I will remember.
Okay, because your mic, sometimes I can hear what you're saying, and most of the time it's really muffled. It's like your microphone is messed up. But all right, so that's about it, I guess.
No, Noah is available to come.
Okay. So we got like 4 people. Good to have more, but basically that's all right. If anybody else wants to go, just let me know. I think that'd be
Professor, I would also like to join that.
okay. Do you need a ride?
No, I'll be able to drive myself.
Okay, and I sent out the map too, so I got 5. All right, because I have to send them the names of the people. So, all right. And if you guys know anyone outside the class or anything like that, they can go too. But I need to know their names probably by tomorrow or something, so they can email Ryan and let him know. I'm pretty sure, like I'm 70% sure I'll be in on Friday, you know, but I think I'll be okay. But I'll let you know like early tomorrow morning. I'll test and see where I am. All right, good. Yeah, so let me know if there's anyone else. Like 5 is pretty good. It'd be good to have 8. So it'd be good to have 3 more people, but that's all right. All right, so I'll see you guys later.
Okay, thank you, Prof.
Bye.